Welcome to our Science 206 final project. Today we will be discussing nuclear energy, primarily how uranium is used in a process called fission to generate heat, and how that heat is then used to produce electrical energy for our homes. Some topics that we will be including are atomic nuclei, the fission reaction and how it is controlled, creating energy from mass and how all these processes contribute to powering millions of homes.
First, what is the nucleus? The nucleus is a dense region in the center of an atom. It consists of positively charged protons and neutrally charged neutrons. It contains about 99.9% of the mass of the atom, but less than 0.01% of the volume of the atom. It is held together by a very strong force called a strong nuclear force. By increasing the number of protons in the nucleus, we can get different elements. For example, hydrogen has 1 proton in its nucleus, but uranium has 92 protons. Altering the number of neutrons, however, results in different isotopes of the same element. Since we have a varying number of neutrons, we now have different mass in the nucleus but the same element. The difference in the number of protons and the neutrons is the nucleus contributes to the stability of the atom, and sufficiently unstable nuclei allow for processes such as fission to occur.
In nuclear fission, two key things need to happen: a release of more than one neutron and a release of heats. Such a material is considered fissile when these requirements are met. Both of these properties are found in an isotope of uranium known as uranium-235. The number 235 refers to the number of neutrons in its nucleus and is considered fissile material. As the name suggests, fission involves the splitting of uranium nuclei. The key piece of this process is that fission releases heat. This is done by colliding neutrons with the uranium nuclei and splitting them into smaller nuclei. This breaking of the nucleus causes for new, smaller elements to be created, along with some heat and some extra neutrons. These extra neutrons can go on to break other uranium nuclei, sustaining the fission reaction. But where did the heat come from? The total mass of the products is actually less than the original material. This missing mass was actually converted to energy. About 1 kilogram for every 1,000 kilograms of fissile material is lost in this way. This behavior is described by a theory called special relativity. Discovered by Einstein, it states that mass and energy are the same thing. It also says that a small amount of mass contains a large amount of energy. This large conversion means that only a little bit of uranium mass is needed to generate a large amount of heat, which is why this technology is so efficient with a relatively small fuel source.
Control rods are highly effective neutron-absorbing structures which are inserted or withdrawn from a reactor's core to maintain its desired fission rate. When the fission rate of a reactor is deemed too low, control rods are withdrawn from the core. This allows more neutrons to accelerate the fission chain reaction. Similarly, the control rods are inserted into a reactor's core when its fission rate is deemed too high. Neutrons become absorbed by the control rods before a fission reaction is induced, and the reactor's fission rate is decreased. Control rods play a critical role in maintaining the safety of a nuclear reactor. However, it is important to note that there is a delayed response between the movement of the control rods and a reactor's fission rate. This is due to the presence of delayed neutrons released from the unstable nuclei that decay seconds or minutes after the original fission. These delayed neutrons induce further fissions, which ultimately delay the change in a reactor's fission rate.
But how does a reactor work? In a boiling water reactor, the heat generated by nuclear fission boils the cooling water passing through the core and produces high-pressure steam. A pressurized water reactor operates similarly to a boiling water reactor, but the cooling water inside the reactor vessel doesn't boil as it is under extreme pressure. Instead, an external water pipe enters and exits the containment structure. As the water flows through the containment structure, it interacts with a heat exchanger. The heat is transferred from the cooling water to the water in the external pipe. The net result in both types of reactors is the production of steam that flows from the reactor to the high-pressure steam turbines, where steam does work, spinning the turbine blades. The rotational energy of the turbine blades spins a magnet in a coil, producing alternating current. The steam then passes through a steam reheater and multiple low-pressure turbines to extract the maximum amount of work from the hot gas. From the low-pressure turbines, the steam flows through the condenser and returns to its liquid state. The water is then directed back towards the reactor core and is reused for further heating.
Thank you so much for listening, and we really do hope that you enjoyed our presentation on nuclear energy.